Good evening, everyone. In the past lecture, we discussed one of the unconventional sources of energy, that was CBM. Now, moving on to the other types of unconventional resources. In this particular lecture, we are going to talk about shale reservoirs. Starting off with the distinction between conventional and unconventional, which I skipped in the earlier lecture. Unconventional reservoirs are those reservoirs from which resources are generated using special techniques like horizontal drilling, well stimulation, fracking techniques. Uh, Such sort of special techniques are to be utilized because of the special characteristics of these unconventional reservoirs. That is, they have ultra low to low permeability of the scale of nanodarcy. So to produce our reserves from such a reservoir, we need to inculcate such special techniques. And reservoirs above zero point 0.1 millidarcy of permeability are generally classified as conventional reservoirs. Okay, so that was the major distinction between your unconventional and conventional reservoir from definition point of view. So as you can see here, we have a conventional well in which the all the oil and gas that was generated in our source rock, it has migrated towards under the effects of buoyancy and capillary pressure. It has migrated to a reservoir rock and it has trapped under the reservoir trap. So we drill into our reservoir rock and we take production. This is the normal method. We drilled a vertical well into the formation and we started taking production. But a lot of oil and gas is still stored in the unconventional reservoir. That is, let's say, in the case of a shale reservoir, in the form of adsorbed gas, as well as the gas that is present as free gas in the natural fractures of the shale rock. So to produce that, we incorporate special methodology. That is, instead of a vertical well, because if you will drill a vertical well and you make a perforation here, because of the ultra low permeability of the shale rock reservoir, the production from the shale reservoir won't take place because the oil and gas reserves that are present over there, they don't have the flow channel through which they can be produced. So what you can do instead, you can drill a horizontal well here, and then you conduct hydraulic fracturing. You generate artificial fractures into the formation, which will create those flow channels through which now the reserves can be produced. Uh, as you can see here, natural gas will flow through the fracture system. The major distinction between shale and conventional reservoir has been shown here, depicted here in the table. Uh, it is found at deeper depths from 2000 to 5000 meter. Porosity ranges from 5 to 25%. That is, it is basically less porous. And the major distinction is that permeability is very less, of the scale of nanodarcy. While in case of your conventional, we have permeability of the scale of millidarcy. So because of this ultra low permeability, because of this particular reason, we have multiple flow mechanism in case of a shale reservoir. Now, starting from the where how these oil and gas are being generated in our uh, source rock, that is our shale reservoir. So we have a particular range of pressure and temperature in which oil and gas production takes place. There are three mechanisms which the organic matter undergoes under high pressure and temperature condition. First, there will be diagenesis, where oil maturation start taking place. The oil is still immature in this particular phase. Then, as temperature increases and as the organic matter gets more buried down, uh, catagenesis takes place. during this particular phase, our oil and wet gas are primarily generated, and this is what we term as the oil window. Okay. And finally, as more pressure and temperature is increased, metagenesis takes place and only dry gas is left out. The key factors that play the major role in formation of oil and gas and identification of oil and gas zones are how much total organic carbon content is present over there in the kerogen or the shale, what is the kerogen type, depending on the way in under what conditions the kerogen has matured. We define kerogen type, and the thermal maturity, which is denoted by R naught. It is basically calculated as vitrinite reflectance. Okay, so for different range of values, we basically define the thermal maturity and range of values of vitrinite reflectance. Uh, we define our oil as how much mature our oil or gas is particularly is. Okay. So starting with the total organic carbon, this is the major factor used when judging the productivity of the shale. Okay, for threshold shale oil, if the range is between zero point 0.5 to 1, then it's a good shale reservoir that is it will produce good quantity of oil. In case of shale gas, if the shale rock has a total organic carbon content of 1 to 4, that is a good range to consider. Whereas for total organic content, carbon content of less than zero point 0.5, it is a very poorly rated shale rock. Okay. Now coming on to the types of kerogen, we have basically four types of kerogen: type 1, 2, 3, and 4. The type 1 and 2 are formed under aqueous condition, that is, they are formed under aquatic condition, and type 3 and 4 are your terrestrial are formed under terrestrial condition. So based on the types of condition under which they have formed, we define the type of kerogen system. Um, Hydrocarbon potential, talking about hydrocarbon potential, are kerogen 1 and 2 are the ones that generally produce oil and gas. They have high quantity of oil. Type 1 has the most quantity of oil, type 2 with significantly lesser quantity of oil and more gas. Type 3 will have only mainly gas only, and type 4 it has no hydrocarbon potential. Okay. Talking about the origin, type 1 is algal, comes under your algal bodies. Type 2 will be from marine origins, skin of spores and pollen, cuticle of leaves and herbaceous plants. Then type 3 and 4 are basically terrestrial, fibrous woody plant, uh, oxidized recycled woody debris. Okay. Talking about your thermal maturity, which is reflected in terms of vitrinite reflectance, from zero point 0.5 to 0.55, 0 to 0.55%, we have onset of oil generation. That is, no oil has been produced if in the shale or kerogen, if the vitrinite reflectance value is in this range. From 0.55% to 1.1%, we have oil and gas in the kerogen. Whereas if we have from 1.1 to 1.4% vitrinite reflectance, we have dry gas mainly. There won't be any oil. And beyond that, if you have a vitrinite reflectance of more than 1.5%, there won't be any hydrocarbon content present in the kerogen. Okay. Once again, as you can see here, type there's a curve over here between hydrogen carbon ratio and oxygen carbon ratio. Depending on that, we have defined type 1, type 2, type 3, and type 4. Type 1 and type 2, as you can see here, these are the ones that we are mainly interested in. You can see this is gas, this is oil. So these are the ones that are mainly producing oil. The type 3 has little bit of gas, and type 4 doesn't have any quantity of gas. Uh, Type 1 kerogen has high hydrogen, low oxygen rates. Its composition is best organic matter for liquid and gas hydrocarbon generation, as we talked earlier. Similarly, type 2, it is suitable for large volumes of hydrocarbon formation. When it comes to type 3, it is suitable for gas generation, whereas type 4, it hasn't any potential for oil and gas generation. So that was about types of kerogen, and as well as the thermal maturity, which is denoted by vitrinite reflectance, and the total organic carbon. So based on these three main parameters, we can judge whether our particular shale reservoir has uh, good quantities of oil and gas or not. Then again, once this kerogen it matures, bitumen is formed, and from that oil will form, and further biodegradation of oil, biogenic gas will form. There is also if secondary cracking of oil, which produces thermogenic gas. So process in a source rock leading to oil, gas, and carbon-rich residue. This, which is your pyrobitumen, finally pyrobitumen. So this is the entire process through which your oil and gas are being formed. Now, if this particular oil and gas it gets migrated towards lower depths and they accumulate under a trap, which eventually be produced by a vertical well, then that's known as your conventional well, conventional oil and gas drilling. But if you are producing from the kerogen itself, that is the oil and gas that is produced inside the kerogen, they haven't migrated. They were not able to migrate, and they are still there. Uh, that will come under your unconventional reservoirs. So, what is shale gas? Uh, as we discussed earlier, since the oil and gas is getting produced there, and we are producing from there only, there is no migration. So the source and reservoir rock is the same, as well as it is acting as a seal. That is the oil and gas that is generated inside it. It is not being able to expel out of it. So it's altogether the source, reservoir, and seal rock. Okay, and it is rich in organic content. So shale gas is a self-contained hydrocarbon system. Talking about shale gas, we have gas in the natural fractures of the shale reservoir, which is our free gas. Then we have dissolved gas inside the matrix of the shale. Then we have adsorbed gas, that is adsorbed onto the surface of the shale rock. uh, when we start taking production, when we create this artificial fractures into the system, the free gas that is present over there in the natural fracture system, initially it will get produced. And once, just like in the case of CBM, once we have produced a particular quantity of gas from it, the pressure will deplete. And once the pressure goes down below your critical desorption pressure, the adsorbed gas that is there in the system, it will start getting desorbed from there. Okay, so now we'll see how that works. Also, the adsorbed gas that is there, adsorbed onto the matrix of the shale, it increases with pressure and as well as an amount of organic matter. So as your total organic matter is increasing, you can see that more and more quantities of gas is being adsorbed onto the surface. Okay. Now coming on to the flow mechanism, which I discussed earlier. So you can see you start taking production from the well. Initially, there will be flow in the fracture system, then flow in the matrix system. Once your pressure drops below your critical desorption pressure, the gas will start getting desorbed. Uh, so it takes place like that. So this is a sort of conceptualizing what I've just told you. There is adsorbed gas onto the organic matter. This sphere I'm considering as my metric system. This is my cell in the simulation. So, uh, so as you can see that initially when I start taking production, a free gas is produced from the vertical fractures. So this vertical fracture is my artificial fracture that I've created. Uh, then as the pressure decreases, the free gas that is present over here in the matrix in the natural fractures, it will start getting produced. And once critical desorption pressure is reached, gas start dissolving from the matrix and feed this natural fracture system, which eventually feeds your artificial fracture, and gas moves through your horizontal well. Okay, so you can see here uh, how production is taking place through vertical fractures, once then through natural microfractures, and then once critical desorption pressure is reached, your gas from the system, it will start getting dissolved, and it will also start getting produced. So the total gas that you are producing from the system is basically your free gas plus your adsorbed gas. Okay. Now, free gas can be calculated through your volumetric method. This adsorbed gas, it can be calculated using either of the model. It can be calculated using Langmuir isotherm model or Frendulich isotherm model, depending on how you are modeling your system. Okay. So what does hydraulic fracturing involve? So a horizontal well is drilled through the source rock. Okay, we have drilled a horizontal well. Cement and casing is installed. I'll install my casing, then cement it. Then I'll perforate my well. Small fractures through casing are created by explosive charges. Now, once such small fractures are created, I will inject high pressure water. I'll inject my water and propellant under high pressure into this small fractures, and under the effect of such high pressure, these fractures, these small fractures which were earlier there, they will extend, and the hydraulic fracture propagation will take place, as you can see here. Propellant, which is mostly sand, it will remain in the fractures and keep my fractures opened up, so that the flow keeps on so that the flow continues without any abruption. So that's how I'm taking production. Okay. This we already discussed that gas volume in shale is sum of your free gas and gas adsorbed on the surface of kerogen. To determine this volume in the lab, what we basically do, this free gas we generally account using the help of petrophysical methods like logging. We use gamma ray logs to find zones which contain shale. Gamma ray logs having, let's say, more than 150-degree API, those will be our shaly zones. Then using resistivity logs, we can find zones which contains your gas. Zones having less resistivity will be the zones having gas. Okay, so that's how you find your system. Then once you take a core sample uh, and you put it in a canister at reservoir condition, the volume removed from the canister is measured volumetrically. Isotherm experiments give estimated amount of adsorbed gas. Okay. Free gas in the reservoir is estimated using petrophysical logging operation using porosity and gas saturation. So eventually after resistivity logging, you can utilize your density density logging or neutron logging to estimate porosity and eventually saturation of gas. Okay. Thermal maturity is measured by vitrinite reflectance, as we discussed earlier. Measurement excess of 1.5% gives an indication of dry gas generating source rock. Okay. A reflectance below 0.6% is indication of immaturity of kerogen. So between 0.6 and 1.5%, we are getting our oil and wet gas. Above your 1.5%, we are getting shale gas. Below 0.6%, our kerogen is still immature, and no, it is still under diagenesis process, and the production of production of oil hasn't, sorry, the catagenesis process hasn't still taken place. Now coming on to shale oil. Just like shale gas, we have shale oil as well, which is the oil that is stored inside my shale rock. Now it's not like gas, and that is, it is present inside very low permeability, that is of the scale of nanodarcy shape. My oil is inside that, and it can't flow outside. So what will I do to extract this oil outside, out of the shale? Well, what we basically do is, we mine it and we heat it up, and after heating it, we further upgrade our oil, and then we send it to the refinery. So that's how shale oil is produced out of shale. Key takeaway is that this type of kerogen falls under category 1 and 2. This we have already discussed, which is basically from lacustrine and marine algae. Then this is how we are extracting. We are mining the shale, then we crush it, then we put it up in a retort chamber in which we heat it up to high degrees. Then we upgrade our oil before we send it to the refinery. The shale that is left after extracting oil out of it is the spent shale, and it is sent to disposal site for reclamation. Uh, Whatever I have explained here, it has been written over here. Uh, so that was all about shale oil and shale gas. Okay. Uh, Now we'll discuss about gas hydrate. Thank you.
Oil and gas typically begins with a muddy mix of fine sediments, such as silt and clay, combined with the organic remains of aquatic microorganisms called plankton. This organic mud can accumulate across wide areas offshore or on lake bottoms in locations where plankton is abundant. If the organic mud becomes covered by other sediments, it will compact into a type of rock called organic shale. If the organic shale becomes deeply buried over millions of years, it will become exposed to increasing levels of the Earth's heat, and the organic matter will begin to convert into oil and gas. Shale that has formed oil and gas is called source rock. The silt and clay grains in shale are tiny and stacked in a tight pattern, which makes the rock nearly impermeable. As a result, if a well were drilled into source rock, very little oil and gas would make its way through the rock to the wellbore. For that reason, it was long thought that it would be forever impossible to produce from source rock. However, a portion of the oil and gas in the source rock escapes over time and can accumulate in areas where it's easier to produce. Here's how that happens. Deeply buried rock layers that were deposited in an aquatic environment typically still have water rather than air between the rock pores. Oil and gas is lighter than water. Accordingly, if the oil and gas that escapes the source rock encounters porous and permeable rock, such as some sandstones or limestones, buoyancy will force the oil and gas upward through the pore spaces. If the oil and gas encounters an impermeable layer that blocks its upward migration, it may begin a lateral migration along the layer boundary. If the migrating oil and gas encounters a trap-like structure that it can't escape, then oil and gas will begin to accumulate in the trap in the pore spaces between the rock grains. Traps are often created by faults or folds in rock layers. The structure shown is an upward rock fold called an anticline. This is called a conventional oil and gas trap. A conventional trap can usually be developed with vertical wells because it contains a concentrated accumulation of oil and gas, a much higher concentration than in the source rock. The rock is porous, meaning that it can hold a lot of oil and gas, and the rock is permeable, meaning that oil and gas can flow through the rock into well bores. Isolated traps can be spread over a wide area where source rock is present, but not all structures that look like traps on seismic will contain oil and gas. As a result, conventional oil and gas drilling results in isolated areas of productivity, and a lot of risk is involved in finding those areas. Nonetheless, most of the conventional oil and gas areas in the United States have been extensively explored over time, and the most attractive trap-like structures have been drilled and largely depleted. Around the year 2000, a combination of strong oil and gas prices and advances in horizontal drilling and hydraulic fracturing technology began to make it economically feasible to produce from source rock layers or other poor quality rock layers that contain migrated oil and gas, commonly called tight rock. For example, most of the drilling in the Eagle Ford and Marcellus areas is shale source rock, whereas most of the drilling in the DJ Basin and the Bakken is into tight rock. Shale and tight rock layers easily accommodate horizontal drilling because they span wide areas with few interruptions, allowing large working areas without dry hole risk. However, layer thickness and characteristics are not always uniform, causing some areas to be better than others. Horizontal wells are drilled down vertically, or mostly vertical, until they get near the targeted formation and are then curved into a horizontal direction and run long distances laterally to give the wellbores extended exposure to the formation. For example, a vertical well piercing a 100-foot thick shale layer would only have 100 feet of exposure to the oil and gas interval, whereas a horizontal well would have several thousand feet of exposure. Hydraulic fracturing further extends the drainage pattern around horizontal wellbores by creating fracture patterns that facilitate flow.